It's always neat when we can get introduced to someone new in the industry, especially when they have great credentials and can talk intelligently about something that helps us do our jobs better. And Mersedeh Naji from the Dielectric folks is with us today, and she's going to talk to us about a new antenna that came out this past spring, and some other things, I guess. So let's turn our attention to Mersedeh. Hi.
Hi everyone. Very glad to be here. Thanks, Barry. I hope you enjoy my presentation. I try to keep it short and I try to keep it interesting. So I hope you find it that. Um, can I share my screen, Barry?
Absolutely. There you go.
So do you have my screen?
We do, but we just have miniaturized. You might want to enlarge it. There
Okay.
you go.
Okay. Awesome. Okay, so in this presentation, I'm going to introduce you to the new panel, FM panel that we developed here at Dielectric. It's a high power broadband circularly polarized FM panel. In this kind of category, it's our first panel. I'm going to introduction over in general dipole designs that they're used in FM broadcast. And then I'm going through the conceptual design of this idea that we had, how to develop this high power broadband circular polarized panel. And then at the end, I'm going to introduce you to the performance characteristics of this new panel, such as VSWR, the azimuth pattern, the HP ratio, and the power handling of the new panel. Historically, broadband circularly polarized FM panel antennas, they all utilize a rotating phase, and all designs that we see on the market today, there are in some of the variations or any of these variations, including the quad dipole panels, horizontal/vertical dipole panel, or a plus or minus degree 45-degree dipole panels. And in all these cases, the panels either have 2 or 4 inputs. And they can be made into single input, but that would require a hybrid. It both simplifies the system, but it also adds unreliability because the higher number of components and cost to the system. And in all cases, the panels have 4 balun tubes. The feed system comparison between a quad dipole panel and a horizontal/vertical dipole panels are as such. In a quad dipole panel, we need at least one 2-way power divider and a pair of 6-way power divider plus phase cabling or adding phase or cables or designing phase through the cables. In a horizontal/vertical dipole panels or plus or minus 45-degree dipole panels, we only need one 6-way power divider, and it doesn't require any phase cabling. So we thought about this and we thought that what if we could design a broadband panel with a single input without the use of hybrid and only use one balun tube? In order to do that, I'm not going to bore you with all these math, but phase cabling. So in the slides, you just need to get the idea that in the impedance of a dipole, the both real and the imaginary parts of the dipole input are both functions of the dipole length and the dipole radius. That's all. In this figure, which is the result of the last slide, you can see that with the increase of in the dipole length, the impedance at first becomes capacitive, and then with the increase of the length, it will become only resistive at the resonant frequency, and then later on it will become inductive. So with just the length of the dipole, we can control the impedance. So as the phase, with just the length of the dipole, we can also control the phase. So when a dipole length is 0.52 lambda, it'll radiate 90 degrees ahead of a dipole length of 0.43 lambda. So these are the results of those. Well, with these idea, the DCPC panel was born, which is a single input, single band tube, circularly polarized panel. But the problem is the bandwidth of this panel is narrow. It's only 3 megahertz. So we need to increase the bandwidth. In order to do that, we need to look into the impedance matching closely. So in our traditional DCPJ panel, we just use a simple transformer in the main balun as our matching network. But in this case that we need to achieve higher bandwidths, we need to go with a more complex, more intensive impedance matching network. So what can we do about that? The first step, the simplest step, is to just make the dipoles bigger, and that's what we did. We went from 1 inch dipole diameter to 3 inches dipole diameters, and we gained 4 megahertz more bandwidth. So we reached to 7 megahertz bandwidth in total. Making the dipoles bigger in diameter, it lowered the Q factor, and lower Q factors means higher bandwidths. Next step was the short circuit stub. Well, using a short circuit stub for impedance matching will help us to, that circuit stub would act as a transmission line, and it will act as a reactive component, and it can be sized and positioned to cancel out the reactive components of the load impedance. And with this method, we can effectively button the bandwidths. Well, with this method, we achieved another 3 megahertz of bandwidth, and we achieved around 12 megahertz of bandwidth with the short circuit stub. And last but not least, we added the parasitic element to cover the whole FM bandwidth. So the parasitic element, it can be a rod, it can be a cone, it can be a disc that goes over the top of the panel. It's not fed, so it's a passive element, and it resonates at a slightly different frequency than the main panel, and it results to broaden the bandwidth. As you can see here, with all these three, we were finally able to cover the whole FM band from 88 to 108 megahertz. So to summarize that, to achieve this high bandwidth in a simple single balun panel, dipole panel, we did 3 things. We increased the dipole diameter, we added a short circuit stub, and we added a passive parasitic element. But how about the performance? Well, in HD polarization ratio is function of differential dipole length, and I just mentioned that we had that polarization matched so that it will radiate at 98 megahertz. Both vertical and horizontal azimuth patterns would be the same, meaning that the HV ratio at 98 megahertz is 1. But since the length of the dipole affects the HV ratio, and that depends on the frequency as well, that means that at 88 megahertz, the HV ratio would drop to 0.67, and at 108, megahertz, the HP ratio would be 0.45. So we needed to figure out a way to keep these this HP ratio basically stable across the band. That was again another idea. Is in a two-layer configuration, we rotate the second panel 90 degrees and feed it 90 degrees. And with this method, we were able to have that stable azimuth pattern across the whole FM band. You can see the results in this figure. This is the azimuth pattern, and so it's a two-layer, three panels around configuration. And as you can see, since the H and V are a little bit twisted with respect to each other, the whole composite pattern is more circular compared to our CBR panel, which is another dielectric product. Another good point of this new product is the high power handling. So in traditional broadband FM master antennas, they all need to handle a lot of power. And in conventional designs, the parts that they are bottlenecks and they makes it unreliable, makes the panels unreliable to handle higher powers are the balun tubes and the feed straps. So these components are removed. So we have fewer balun tubes and we have no feed straps in the system. And that means that our panel is able to handle higher powers. We applied in this scenario that we tested and simulated in HFSS. We applied a 10 kilowatt power to this panel, and the measured peak voltage was 4.11 kilovolt over centimeter with respect to the air breakdown threshold, which is the voltage threshold that the material becomes ionized and it'll become plasma, basically. We don't want that to happen. And so our voltage safety factor with respect to that would be 5.5, which is very, very great. So in conclusion, you can see in this picture, actually, that's the finished product. That's my colleague, Dave. It's a small panel. Well, that's one thing. More importantly, it's very reliable because we significantly reduce the number of elements. We don't need many power dividers. We reduce the number of balun tubes. Also, the system doesn't need any feed lines and hybrids and feed straps. So all of these also means cost. So it's less expensive. I will be glad if you have any question, please ask me.
All right, anyone that has a question, just hit your space bar or alternate A. And I think the idea of being able to use fewer components and handle the power is a very good one. It also reduces the potential for problems. What kind of total power handling would this antenna handle?
Well, we tested it up to 25 kilowatt and kilowatt, sorry, excuse me. But this test result that I put in my slides was for 10 kilowatt. So I mean, even up until 25 kilowatt, it was still safe. And yeah.
Well, that's good. Yeah. And so the efficiency is a couple of percent higher than what would normally be expected.
Yep.
So, well, let's just pull something out of the hand. You said you did with a 10 kilowatt power. What kind of ERP would you gain?
We usually look at the current density in HFSS. So like that's our measure basically. Yeah, so yeah, that was and well, the part that it was, uh, the important things about the multi-safety factor for us was to not make it so hot and not make it plasmatic, and that's what we gained. So we,
So Barry, this is John Schadler from Dielectric.
Hi, John.
Hi. I can just add a little bit more to to your question.
Please.
Certainly what Mersedeh is talking about is the power handling of an individual panel. When you actually use these panels, they're used in an array. As far as the azimuth pattern goes, it can be an omni with 3 around. It can be very directional with just 1. It can be 2 for a cardioid. And it can be up to 8 to 10 layers high. So you multiply the number of panels by 10, and you can imagine the amount of total input power that this can handle. As far as ERP goes, again, depends on the azimuth gain and the elevation, number of panels high. So, certainly 100 kilowatt ERP is easily achievable with about 6 layers of 3 around Omni.
Okay.
As long as you have the TPO of around 20 to 30 kilowatt TPO.
Fairly normal.
Yep.
But of course, I suppose one of the benefits, of course, of the efficiency is power reduction.
Yep. Yeah. I mean, the whole purpose of this development was it really does everything that a very expensive, high power, cavity back radiator style master antenna does. But those antennas, as Mersedeh said, have 4 Ballon tubes. They have feed straps, twice the feed system. They usually use hybrids, and all of that is removed with this. So we have it's the first panel that's been developed that is broadband across the whole band for master antenna use, or combining channels. That basically has a single input, no feed straps.
I think it's interesting that when you went to a larger diameter on the dipole, there appeared to be 2 minimum SWRs, and I had never thought of that. I thought it would just make it broader.
Yep, basically you're adding more and more resonance points by adding more components, if you will, whether capacitors, inductors, to your matching network. So the more you add to the circuit, the more poles or resonant points you can have.
I was looking at this slide. It is apparently only about dipole diameter, or is there more to it?
That first one you see there is just increasing the diameter, showing you how much more bandwidth you can gain by doing that.
Okay, and it does result in a double minimum.
Correct. It's as if you created a loop in the impedance on the Smith chart, and that loop then goes through the middle.
Interesting. Thank you.
Any other questions that you'd like to pose? I think one of the things that a lot of people, and I mentioned this in the newsletter, once an antenna is installed, that's as close as most engineers ever get to them. They're up there, a couple hundred feet, couple of thousand feet. And so the idea of the antenna wearing out doesn't really occur to anybody. So let me ask you, what would the presumed lifespan of this particular antenna be, as opposed to, let's say, something that's been up in the air for 20 years?
I mean, certainly.
Sorry, you go ahead, Jim.
I guess you can look at it as a comparison. If you look at panel antennas, they're always less reliable than other styles. And that's because of the number of connections, the number of feed lines, the number of power dividers, number of components. reliability is directly proportional to parts count. And also in an RF system, the weakest link is always a joint or a connection. And with using this type of panel and eliminating a large portion of those, I mean, in terms of actual parts count, you're probably in the neighborhood of 80% less than a typical CBR. You can imagine the reliability is just that much more. As far as a lifespan, a lot of that depends on how much power you put in, depends on the environmental conditions, depends on maintenance. It depends on a lot of things. Has the system lost pressure over the years? It has moisture ingressed into the system. There's so many variables. It's kind of hard to even put a number on what you're asking, but certainly by reducing the pinch points, you're making it inherently more reliable.
Well, actually, what you're doing is answering my question more than you thought, but you're achieving what I'm asking, and that has to do with what do you need to check over the years? What you're talking about a checklist of things. I think that's an excellent thing to provide, because if somebody comes into a station and they're not the original engineer, they really don't know what went into that antenna, and to know what they should check is probably a good thing, especially the younger folks.
Yeah, you mentioned pressurization, which of course should be watched continuously. There was also the thing of air breakdown and so on, which would be what related to the power level. It seems as though the lifetime should really be unlimited unless there were, some failure like pressurization or an insulator breakdown or something. But as Barry is saying, what sort of maintenance would there be other than make sure you keep this thing pressurized?
Yeah, well, you really shouldn't need any maintenance. This it's made of all materials that resist as much corrosion as you can resist. Stainless steel, copper, brass, so on. But there are environmental conditions that will eat away, if you will, or corrode a system, no matter what it is. If you have a very salty environment, it's going to, obviously metals do not last forever in those environments.
Well, that's true. And you have everything from the desert dryness to the salt water on the coasts and everything in between. I think one of the things that, of course, a lot of people forget is if a lightning strike occurs, one of the things that probably is a little harder to detect when these things happen is to know when something is changing. And I think this, in my mind, relates to the amount of attention being given to the parameters, that you don't just let the thing sit there for 6 months to a year between checking on it.
Right. And there are ways of monitoring your system to keep an eye on those types of things, and also monitor for degradation of your transmission line and the antenna itself. We've got quite a few products that do that. The Hawkeye is one of them, which is a continuously basically off frequency monitoring system that, again, you have alarms that would show you any type of degradation anywhere in the system.
So these, if you were running just one level, you would typically have power splitter driving 3 panels and so on. And the power splitters, I have done nothing with panel antennas. So the power splitters are up there on the tower next to the panels. Is that correct?
Correct. Yep. And the slide that Mersedeh showed, that was just the power dividing system that you would need for one layer. So you can see how complicated it is for, say, a quad dipole system. That's just for one layer. And then it simplifies to about half of that with crossed dipole designs. And it's dropped again in half by using the single input design that we're showing.
So would you recommend this for an existing multi-station installation or a newer one?
Either one.
I'm trying to dance around asking the question purely in terms of money, but if you have an older system, what is the incentive for them? If it's been operating all right, what is the incentive to move up to this?
Well, a lot of the older systems, they may have limitations. They may have limitations in terms of, power handling, number of combined stations. Do they handle IBOC? All those things may drive you to a new, a new design, a new installation.
And again, this is a sort of thing to learn about so that you could determine if your existing antenna is going to benefit.
Correct.
I'm going to guess that you would typically replace an existing one with this if you were adding more transmitters and needed additional bandwidth and so on, and perhaps power handling capability.
Yes. Yep.
Mm-hmm. How many of them are any of them in the field as yet, I should ask?
Not as of yet. We're actually we're testing serial number 1 right now. We'll actually do some power testing on our roof to make sure that we didn't miss any weak spots. We'll build the whole system in the back on our deck, and we will test the entire system after we test each individual component. So that should ship within the next month and a half.
Very good. Well, I hope you will come back and let us know how it's been received in the field.
Would love to.
I have no experience with panel antennas. How do they behave in icing and other weather conditions?
Well, the beauty of a broadband system, as Mersedeh mentioned, that means that the Q is very low, which means that you can shift the impedance due to environmental conditions, and it still remains, the VSWR still remains stable. So the broader band you are, you can shift the impedance around, and basically it doesn't change anything. If you have a very narrow band like that notch that you saw in the original one, and you move that notch, you can imagine how quickly your impedance changes. And that's what happens. You add ice, it makes the dipoles look longer, shorter, thicker, and you basically are shifting that impedance.
Very good. Any other questions from the field? It looks like
It's one last comment. I think some of the ideas, well, actually all the ideas are very clever, especially the thing of getting the vertical and horizontal fields to agree by just swapping antennas, and that's clever.
Yeah, it's a relatively simple technique and an aha moment. But since the nature of how this is built with the rotating phase, which is achieved by the differential dipole lengths, you can basically turn this thing 90 degrees, and the horizontal becomes the vertical and the vertical becomes the horizontal. So basically you're flip-flopping the two every layer. And then if you put it back in phase with the 90 degrees, horizontal goes back to vertical and vertical goes back to horizontal. So, and you take the average of the two, and they always equal 1.
Very good. All right. Do we have, on that last slide that you had there, is there contact information that we should show here?
Unfortunately not, but I will send out contact information definitely.
Okay.
Excuse me.
We certainly appreciate your taking the time and the description here. And as Harold says, it's a very innovative way of looking at what people say. Well, we've been using these antennas for 40 years, 50 years, whatever. And now there's something new, something to benefit from, and that's good.
Sure, and I forgot to mention this is a patent pending, so yeah, I forgot to mention that. Thanks for the time, and yeah, thank you.
Okay. Come back, talk to us again.
All right. Thank you, everybody.